So welcome back to my lectures on Introduction to Galois Theory. We are coming to an end of this entire course on Galois Theory. Our last session is on Insolvability of Quintic. The insolvability of Quintic. So before we get into the details of this chapter, we need to find out what exactly we are talking about here. We know if f is a field and f of x belongs to the ring of polynomials, then we can find an extension of f such that all zeros of f of x belongs to E. Definitely this is possible. Quintic means a degree of 5. So here it means that we're talking about a polynomial of degree 5. Well, insolvability does not mean that it cannot be solvable because of this. We already know that if you take any polynomial of any degree, we can find an extension of f that contains all the zeros of f. So this has got a different meaning here. So we are actually looking for an extension of f, a particular type of extension of f. So what the theorem is going to say is that we cannot find such an extension. We are going to explain what that extension is. We cannot find such an extension where we cannot find all the zeros of some polynomial of degree 5. Meaning there exists some polynomial of degree 5 whose zeros does not belong to a particular type of extension of f. That does not mean that all the does not mean that all the polynomial of degree 5 are like that. There are polynomials of degree 5 whose zeros may belong to such extensions. So let us get into the details of what kind of extension we are talking about. So we'll start with some examples. By the way, we are going to talk about only those fields whose characteristic is 0 in the whole chapter. We are not going to deal with any other kind of fields. So if I didn't mention in anywhere, you should assume that all the fields are of characteristic 0. For example, Q or R or C, these are all fields of characteristic 0. Now, we are going to talk about special kinds of elements called radicals. And we are going to take the base. This is an example, okay? Examples. We are going to take the base field as Q. So, an extension K of F, an extension K of F is called a extension of F by radicals if every element of K can be expressed as finite operations of additions, subtractions, multiplication, division, and nth root of elements from F. This is not the formal definition of extensions by radicals that we are going to come here, but I want to, this is easier to understand what I'm talking about here. So let us start with this and give some examples, then we'll come to the formal definition of the extensions by radicals. So if you take Q, Q root 2 is an extension of Q by radicals, because any element of this will be A plus root B, root 2B, or B root 2. That is actually finite operations of addition. So A plus B root 2. These are all actually finite number of operations, definitely. This element is from Q, this element is from Q, and this element is from Q. Not root 2, but this element is from Q. So we say that nth root, this is actually square root of 2. So this is a finite operations of addition, subtraction, multiplication, and division. We'll take another example here. Q of root of 1 plus root. This is also a finite operations of addition, subtraction, multiplication, and division, and the nth root. So how many operations are there? 5 operations. These operations should come only finite number of times. Actually, the first operation is the whole root. So this is my first operation. And this is my second operation. and all the elements are from Q. So this is also an extension of Q by radicals. So the thing is, we are going to form a formal definition for this. The way we are going to do the formal definition is, and I'll come back to here to explain what I'm talking about here. So let F be a field with the characteristic 0, which I already told you that you're going to consider only field of characteristic 0. Then an extension of F is called an extension of F by radicals if K is equal to a finite extension alpha 1 dash dash alpha r, and, or can say, if there exists alpha 1 dash dash alpha n belongs to F and integers, not n, alpha r, and integers n1 dash dash nr such that K is equal to finite extension of F with alpha r elements, such that alpha 1 of n1 belongs to F and alpha I of ni, alpha I to the power of ni belongs to F of alpha 1 dash dash alpha I minus 1. This and this are equivalent. What I'm trying to say is, for example, here Q of root of 1 plus root 2 is actually equal to Q of root 2 comma root of 1 plus root 2. These are same. Because root 2 belongs to this. And here, this is our alpha 1. And this is our alpha 2. Our n1 is equal to 2, n2 is also 2. So these two are equivalent because our alpha 1 is 2, so alpha 1 square is 2, which belongs to F, so that is done. Then we need to show that alpha 2 belongs to this. Alpha 2 is equal to root of 1 plus root 2. So this actually alpha 2 square, because n2 is 2, is equal to 1 plus root 2, and that belongs to Q of root 2. And that is what this one is. So Q of root of 1 plus root 2 is an extension of Q by radicals, because this can be expressed like this. So this is the formal definition of an extension by radicals. Now let us come back to our original question of insolvability of Quintic. We know, actually we are looking for zeros of a polynomial in an extension of extensions by radical. We know that if f of x belongs to f of x, then there exists an extension e of f, such that E contains all zeros of f of x, and smallest of such extension is called the splitting field of f of x. So definitely there is an extension, but what we are interested is not any extensions but extensions by radicals. So the question is that there exist polynomials of degree 5 such that its splitting field is not an extension by radicals. That is the meaning of insolvability of Quintic. See, for example, x to the power of 5 minus 1. This is not a Quintic which we are talking about. The splitting field of this polynomial over q of x is solvable in the sense that the zeros of this polynomial are in the extension of q by radicals. For example, here if zeta be a primitive root of unity, then q of zeta is the splitting field of x to the power of 5 minus 1. And of course, this is a extension of q by radicals because here alpha 1 is equal to zeta and n1 is equal to 5. Zeta to the power of 5 is equal to 1. That means q of zeta is an extension of q by radicals. So we already have a polynomial of degree 5 whose zeros belong to an extension of q by radicals. Or in other words, the splitting field of the polynomial is an extension of q by radicals. So only sum of the polynomials of degree 5 does not belong to this kind of stuff. Like if you find the splitting field of that polynomial, then splitting field is not a extension of q by radicals, and that is what we are going to show. We need some definitions and results from group theory before we proceed further on this session. So let us start recapping some of the definitions and results what we need. Group theory. The first definition is that a group is simple if it is non-trivial, meaning it has got more than one element, and does not have any non-trivial or non-proper normal subgroups. Second definition, a subnormal series of a group G is a finite collection of Hi, I is equal to 0 to n, collection of subgroups of G such that H0 is equal to the trivial subgroup with one element, and Hn is equal to G, the whole of G, and Hi is a normal subgroup of Hi plus 1. The next definition is a subnormal series of a group G is composite if we'll write it as like this: series Hi, I is equal to 0 to n, subnormal series of group G is composite if every factor group of a factor group, will say, write it as Hi plus 1 over Hi, the factor group of the series is simple, meaning it has got the same kind of finite collection of subgroups, and in subgroups these are actually normal, so we can definitely talk about the factor group, and those factor group has to be simple, should not have any normal subgroups. Now, next definition is a group is solvable if it contains a composite series where every factor group is abelian. So this directly goes another result here. A finite abelian group is solvable. Another result is a homomorphic image of a solvable group is solvable. So these are the definitions and results we need to go further on our theory of insolvability of Quintic. So before going to prove the main theorem, we need to establish some preliminary results. So the first preliminary result that we are going to attempt is this theorem. Let F be a field of characteristic 0, and for an element A in F, let K be the splitting field of x to the power of n minus a. Then the Galois group of K over F is solvable. So there are two cases here. Case 1 and case 2. Case 1 is, let us assume that n is equal to 2 and n is equal to 2 and a is equal to, let's say, 3. So x to the power of n minus a is x square minus 3. The second primitive roots or second roots of unity, second roots of unity, I'm actually going to assume that f is equal to q. Second roots of unity or q are plus or minus 1 and both belongs to q. This is the first case. Second case is, let us say n is equal to 3 and a is equal to 2. It is x cube minus 2. So the third root of unity are, one is 1, another one is minus 1 plus root 3i by 2, another one is minus 1 minus root 3i by 2. These two does not belong to. So there are two different cases. So let us take the first case. Case 1. Let all of the nth root of unity are in F. That is the first case. So what we do is, we want to show that G, the Galois group of the splitting field, is solvable. In other words, what we are going to prove is that Galois group is an abelian group. So let zeta be a primitive let zeta be a primitive root of n, primitive nth root of unity, and beta belongs to k be a 0 of x to the power of n minus a. This implies beta gamma zeta beta zeta square beta dash 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 zeta to the power of n minus 1 beta are the distinct roots or distinct zeros of x to the power of n minus a. Here, all zetas are in F. So, any automorphism in G of K over F is then determined by the value of zeta. That means let sigma mu belongs to G of K over F implies sigma of zeta is equal to zeta to the power of I and mu of zeta to the power of j for some I j. And this implies sigma of mu of zeta is equal to mu of sigma of zeta is equal to zeta to the power of I plus j b. No, I plus j. This implies G of K over F, Galois group of the splitting field, is abelian and hence solvable. Case 2, let not all nth roots of unity are in F. Similarly, here let zeta be a primitive nth root of unity and beta be a 0 of x to the power of n minus a. Implies same thing, beta gamma beta, sorry, zeta beta comma zeta square beta dash dash zeta to the power of n minus 1 beta are distinct roots of unity. Sorry, distinct zeros of x to the power of n minus a. Here, we don't know the zeta belongs to F, but beta belongs to F, K, and zeta beta belongs to K because K is the splitting field. That implies zeta belongs to K. So we can consider a simple extension of zeta. So F is a subfield of zeta subfield of K. So the corresponding Galois groups are in reverse order. So it will be G of K over K, that is actually the identity map, the group containing the identity automorphism. Then we have G of K over F of zeta. Then we have G of K over F. So I'm going to take this out and put it as a I. Now, G of F of zeta over F is abelian because determined by zeta. And G of K over F of zeta is abelian because of this, because of the previous case. Because all the primitive nth roots are in here. If all the primitive nth roots are in F of zeta, then this is an abelian group because of this. So we have a subnormal sequence of subgroups of this here. We need to show that the factor group is abelian. Okay, this factor group G of K over F of zeta over the identity group is isomorphic to G of K over F of zeta, and which is abelian. So this part is done. And here this one, G of K over F over G of K over F zeta is isomorphic to G of F of zeta over F, which is already abelian. And that implies G of K over F is